projects from GE, which was earlier known as Alstom Grid. The second part on interaction with the grid is National Grid NG or NIA, Network Innovation Alliance projects, that finished about 2 years back. So this will have mainly how wind turbine and wind farm interact within its own cluster of turbines and within the farm, and then how wind farm and other voltage converter dynamically interact with the interconnected power system. So this is thing I expect to finish in 45 days. This is the instability issues. The context to that you could see about 2012, 2013, that type of time scale. It's when the first generation of offshore wind farm was being commissioned in North Sea. And there were some issues with some of the wind farm, which was not always staying connected to the onshore grid. So there were some issues involved with a couple of wind farms. And that became some kind of, the headline news in some of the medias like North Sea wind offensive, plagued by problems, and then in wind blows, German offshore. So those things that started actually giving the problem, and as it happens with power network, that every time we have some severe disturbance and problem and upset, a new sort of technology area is born and understood. So this is how it also happened. The background were the operational aspects of some of the large offshore wind farms like Wind 1. It was reported that the wind farms did not always stay connected to the grid. So I, as an electrical engineer, thought that's a synchronization issue. So there was no clear reason, but some operational issues with interface technologies were suspected. That means when you are connecting through power converters, are there any control or synchronization issues? So we wanted to understand through dynamic modeling and analysis. At that time, the Alstom Grid had a contract for Wind 2, which is a 900 megawatt wind farm with the Dutch interconnections, this Netherlands transmission system operator. So we had some projects, and then we wanted to see what could be the reason. Are there any harmonics? Are there any phase lock loop instability, or the converter control and wind farm control interactions? Are there any resonance in the AC/DC offshore network? So what we should look for, some kind of electrical oscillations in the network, and mainly we want to see the linear system theory approach, so eigenvalue in frequency domain, and what else. So these are the things that we thought that let's explore based on model and see what happens. So that is a typical layout of some part of the wind farm. You see that 500 megawatt. So what you could see here is this side. There are this is top, we call wind farm area 1 and area 2, and there are about 93 turbines here, 3.6 megawatt each, and this side about 33 turbines with 5 megawatt each. So these are all string, in each string there will be some turbines connected, and these all blue lines are 33 kV collection system. Now we have 66 kV cable, which are very standard, and each of these here is a wind turbine with a transformer, and then it comes to this. So between these two turbines, easily there could be a distance of 800 meter to a kilometer. So kilometer. When you are, on the landings path to Heathrow or Gatwick, you could see many wind farms that way, and it may not be so apparent that the turbine between the two turbines, the distance is 1 kilometer, but actually it is about a kilometer between two turbines, or 800 meters. So now if you think about 1,000 megawatt wind farm and 1 kilometer by 1 kilometer, so for 5 megawatt turbine, you need to have about 200 turbine. Now if we have a square sort of wind field for 200 turbine, So this becomes what? What is the square number? Close to 200 is 196. So 14 by 14, right? So you can have 14 turbines this way and 14. So 14 kilometers to 14 kilometers. Imagine the whole area, 14 kilometers by 14 kilometers, and you got that much of 33 cables, all are running. So it's a lot of electrical circuits and so on. So that's the complexity that I'm just giving that way some idea. So then typically, if we take one particular turbine, as a typical say type 3, so this is the configuration. Everybody knows this, so I don't want to spend much time. So these are all major components. And then what we did on that for some operating conditions, we did the say small signal analysis, and then we found out some of the mode, the eigenvalues, their real part, their imaginary part, the frequency and the damping. You see that it varies from say less than a hertz to 10 kilohertz. So this is the dynamic characteristics of an individual unit, and like that we have many unit. So in this case, we have been doing with 126 turbine. And then if we take some of those eigenvalues mode and see the participation analysis, so at different wind speed, subsynchronous and supersynchronous or synchronous. So these are all the damping and the frequency, and who are the responsible state to participate. This is the collector cable, voltage and currents, right? So they may predominantly participate. The 30 kV cable, voltage and currents, they are more dominant in these sort of modes of 10 kilohertz. So other mode, if we see here again in the different value of the wind speed, there are the wind turbine generator, the stator current, and also stator voltage. They participate into this mode. So you saw those modes right here. So this mode I'm talking about. So mode, etc. So they participate into this. So this is participation analysis source. And we can go to the lower mode, typically at 2 hertz. And there we see the generator turbine, wind turbine rotor, and also that turbine, the twist angle that you have been, this. So it's more on the mechanical side. So they participate into this, and these are the frequency for different speed, operating wind speed, and that will change the rotor from subsynchronous to supersynchronous region. So this is how it all lined up. So what we did actually this, we have all the modes. We name them as a network mode if the participation are coming from the network parameters, generator mode if they're coming from the generator operating variables, and turbine modes if they're coming from mainly the turbine side. And these are all the parameters, and did some sensitivity analysis, and you could see that how some of the parameters are influencing some of the mode, and one can clearly see the grid side converter of the DFIG. They are participating in this mode. So there, and then turbine. So this KW or TW, they participate. So this gives us a clear picture. In the one individual wind turbine, we have about say 40 differential equations. So we'll have 40 eigenvalues and states. So in that, who are the state who are contributing to what frequency significantly? So that gives us a clue that okay, so these are the variables that we could control and tune so that the damping of those becomes very, very favorable. But this is just for one wind turbine generator I'm talking about. So then I do it for all. So like that, you see each of them are one turbine, right? And then it comes to 33 kV, and then we have the transformer, and then there is a transformer, and then this is a 155 kV, and then it goes to a point from where the voltage source converter will convert this to DC, and then there is a DC line that will come to the country's transmission system network. So this side we have 33 with 165 megawatt. This side we have 93 with 34 megawatt. Put together is 500. So this is and these parameters and the distance are real actually from the Dolby 3 that we did. So we did some all frequency classifications. So some of the frequency, they are very high frequency, that is 10 kilohertz range. So they're very high. It's here, and usually they are very well damped. They don't have enough sort of energy to sustain the oscillations. The low frequencies are here, and the medium frequencies are the red. So those are the medium frequencies that we are focusing on, because the other frequencies, they are reasonably damped. So let's focus on this red medium frequency and then see what happens to this, right? Now there, I want to make sure that there are some kind of, a misconception about harmonic instability, and in this, most of the time, these terms are very well known in power electronics community, that we call harmonic instability. Now, if we have to say harmonic instability, we must have the frequency which should be matching multiple times of certain fundamentals, like for 50, 100, 150, like that. But here, what is happening, I don't want to call it harmonic instability. I want to call it a resonance, because the network itself has got inductance, capacitance, and various controls. So that itself is a passive sort of dynamic systems. And if I do the eigenvalue analysis, I can get all its natural frequency. So, and if some of them are very close to our excitation frequency, then resonance appear. So I want to say that more of a resonance, the resonance type of thing. I show you that the frequency that is coming, right? You see that there are 310, 250, and say there is also 9.5. Now this is definitely, they are not the harmonics. The 310 can never be harmonics. It can be either 300 or it has to be 200. So that's the resonance. And these are the medium frequency, how they are getting excited. If we put some, say, perturbation to the point of common coupling voltage, and then do the simulation, and then we see that they are all appearing like this. So that when I did this, and I want to do something as a mode map, like this whole wind farm, you see that. So that here there are two. Mode 1 is 310 and mode 2 is 250. Mode 3 is 50 and then mode 4 is 9.75. So what do I mean by this high and low is actually this should be this high, the purple. This is the point of common coupling and the voltage source converter and impedance, all these things. So this area, any component in this area, when their differential equation, their variables are more predominant in this mode in terms of their participation. Whereas we could see that none of the individual wind turbine, all those things are showing any kind of color here. So this clearly says that these four modes have nothing to do with the individual wind turbine, because they are well tuned. It's the interconnections and the transformer and the cables and all these voltage source converter and connections and so on and so forth. So that's the mode map who participate. That's for one operating condition. Then we move to different operating condition, like sometimes some of the turbines will be up and running, some of them will be down for maintenance. Like if I can only have 3 to 5 turbines from the area 2, all the other turbines are set down for maintenance. So that means the last turbine in the whole string is feeding 5 megawatt, then it has to travel all the distance to this. So that's the most onerous sort of situation. Like that, I can have one area where we don't have those turbines, but only a couple of turbines, and similarly for test 4. So these are all, the number of turbines connected or disconnected. So we came with 4 sort of operating conditions and did the whole exercise that I showed to you. And then this is the frequency of those 3 modes, and this is the damping of those 3 modes for all of test case 1, 2, 3, and 4. And one can see that, for test case 4, that is particularly for this, when many of the turbines on the upper part of the wind farm is down, we now have unstable sort of situation because the damping is negative. So we now want to see this here, how that mode is getting more influenced by the converter control parameters. You could see that here as we move the converter control gain, that main PI gain, and then how those modes are moving more towards the right half plane here. So this is becoming unstable. So that's there. So this is about when you have a type 3 turbine, but in reality, in a big wind farm, it gets yes.
Your model that you are analyzing, it comprises the two areas and the HVDC link and the connection to the national grid, to the big grid.
Right.
How far is your model?
Right. So in the first part, I have just represented, I just targeted at the HVDC point. At the second part, I include the grid. This I'm now doing for the whole wind farm, all the connections and the cables, etc., up to the voltage source converter point. So this analysis is for the whole
Up to the HVDC.
up to
The
HVDC.
DC, you consider it as a constant.
Yes, DC, yes. So this is first part. Then I go in my second half, I'll then include the network.
How many state variables?
This is that one 4,000.
4,000?
4,000. Yeah, because if you have say 126 turbines, so 126 into 40, about 30, 35, and then you have all the transformer and the cable, and we model them as nominal pi. So if you have a nominal pi, so you got two capacitors and one inductor, so three state variables. So like that. So about 3,800 to 4,000.
So basically, you are looking for eigenvalues of matrix 4,000 by 4,000.
Yeah, 4,000 by 4,000.
Yeah.
It's a 3 years long project, so we could not find it overnight. So this is that. Now I go to the other technology, like you have a say 2 gigawatt wind farm, which comes with about 10 years time. So in the first phase, you may have type 3 5 megawatt, and in the last phase, you can have PMSG 10 megawatt. So that combination is possible, like in Dogger Bank or Hornsey, phase 1, phase 2, phase 3. You always have different sort of technology in this. So now if we have the type 4 turbine, so what happens? This is simple type 4 turbine, individual turbine, various block diagram. Everybody knows this. So the controller for the grid side converter, bandwidth will vary between 5 to 20 hertz. And the PLL, the phase lock loop PLL technologies, we used actually 4 or 5 technologies like adaptive notch filter, moving average filter, quarter cycle cancellation, and double decoupled synchronous reference frame. So these 4 type of PLL, and then we put here, and then we'll see what happens. So now for one single wind turbine for type 4, so these are the the frequency lineup. So it starts from megahertz to few hertz. There you see that participating states, this is originating from capacitance and inductance of the network. Damping is there, the megahertz, kilohertz, don't need to worry about. Now here about less than 100 hertz to 5 hertz, the grid side converter, controller and network. And then this 28 hertz is PMSG and message side converter, controller, gain and etc. integral part, they are contributing. And here, this is again grid side converter, controller, converter, capacitor, as well as the DC link, as well as the PLL, phase lock loop, state variable. So they contribute to this frequency. So this is again clear that how this is happening. So now I go to this 2 mode, 300 and 240. So this is where the highest participation, again, the voltage source converter, controller, and here. So these modes are always here. And there are also some contribution from this, but the turbines, they don't. But then I go to another one, you see that 21 hertz and 4.4 hertz, mode 3 and mode 4, they are now getting also spread. Individual turbine, they are also participating into this. So compared to the type 3, if I look at type 4 now, in type 3, I saw that no individual turbine was contributing to that medium frequency. So then that gave me an advantage. I can represent each string as an equivalent generator. So if I have 10 generator, in each of those string, I can have 10 into 5 or 30 megawatt and equivalent thing. So I can very easily simplify from 4,000 state variable to say about 400 state variable, because I knew that in those modes, individual turbine do not contribute. But in this case, for these modes, this clearly says that this cannot be done that way. So we have to think about how we could, reduce the model. So these are all the analysis it shows. So now you see the sensitivity to voltage source converter control gain, and how with increasing gain we have been exciting the instability, and this goes to here. So this is the point of common coupling cables, capacitor, and this impedance. So Kp, Ki. So these are the things that will be vary. So this happens. Another thing I wanted to show you that the grid side converter control bandwidth with PMSD. So if we move the bandwidth from 5, 10 to 20, and with 20, you see that again the voltage is oscillating. So this is how the bandwidth. That means if we make the grid side converter control response fast response, then the interaction between the collection side, the cable side, and to the individual turbine side, is encouraged. So this is how sometimes making the grid side converter control slow, it may help rather than making it fast. So that this is this outer loop, and then the speed of the PLL. The PLL response, it can be 5 milliseconds, and then you see that with 5 milliseconds, this is now more oscillatory. And whereas 20 millisecond, it is, 10 millisecond, this is less oscillatory. So this clearly says with a 20 millisecond, the eigenvalues are here, and whereas 5 milliseconds, the eigenvalues are close. So this also is giving some kind of indirect, say assistance to you that, lots of people say, in the first day, there was a question that during someone was presenting, someone said, well, if you have a fault, you must freeze your PLL. Now, there was a question that whenever there is a disturbance or large disturbance, why do you let your PLL also to contribute? There was a question. So there are some approach that you freeze your PLL. So this is giving you some kind of indirect hint that if you make your PLL slow, sometimes it helps. So PLL does not have to always respond to any kind of thing. So that way it can help even for grid forming grid following cases. So this is the this. Then what I did actually, a lot of combination, like we have a wind farm with essentially 2 area and 4 sub area. So wind farm 1 all defeat, wind farm 2 all defeat, and wind farm 1 all PMSD and PMSD. Then we had a combination of defeat. The top part is defeat, bottom part is PMSG, that is type 4, and then top part is type 4 and bottom part is type 3. That kind of combination with all 4 test cases we did, and we found these modes, how some modes are appearing and some modes are disappearing, how their dampings are changing. So these are the modal thing around that. So the summary of this is that very high frequency mode, electrical dynamics of basic cables, very well, and high frequency modes, wind turbine generator and transformers and cables. So they are all well damped. Medium frequency mode, they are close to second, fifth, and seventh harmonics. So this is where actually, we saw sometimes instability, HVDC control, AC voltage, and wind farm transformer currents. Low frequency mode, less than 50, within the wind turbine generator, interaction between the wind turbine generator, so they are well damped. So this is the summary of this work. So understanding so far, it has got many technologies: cables, transformer, converter, PLL, filters. Their dynamic interactions are characterized as mode, damping, and frequency vary as the operating conditions and current change. The VSC and HVDC control has significant influence, but the model is too large to integrate with standard commercial software for power system stability study for interconnected system. So this needed a further dynamic reduction. We did a lot of work on reduction. So G funded a PhD for model reductions. I don't want to report that work because I want to go to the next part, which is the grid interactions. So this is the work that we did, Lina, Rushni and myself on that. And some work has appeared in journal paper and patent. This is the patent that we filed. And also we have some more things. So now I want to go to the interaction. So let's see, include the big network. So we need to do the modeling of the network and then analysis, and then see what insight and recommendation we can have. So typically, the impedance based approach, we have been seeing a couple of presentations here. So this is your phase voltage ABC, and this is your phase currents, three phase, and that is ZABC, the impedance. So we can, this is in our phase coordinate, stationary coordinate, and if we transform this into part transformations, we go to the DQ coordinate, so that we are stationary. So this is a real, this is a transfer function with the real coefficients. But if we stay in the positive and negative sequence, so then this becomes a complex transfer functions, transfer function with the complex coefficients, and then these are the positive and negative sequence current. So this is how we could do. So how we go from one to another is this. If I multiply this by 1 minus j set to this operator, I get this. And if I multiply this by inverse of this operator, I get this. So now we need to see the impedance, that how grid see the whole wind farm as a variable impedance at different frequency. So this one, so typically this is the positive, negative, this, and then we do Nyquist stability analysis. The limitation is it is only to a single converter to infinite bus scenario. So we always see that. Yesterday I was talking about that when you represent something just Z, then you do not represent the entire impedance and the dynamic influence of the grid. In some presentation yesterday, I mentioned, right? So that is how you could do that. Now in real transfer function, then we can, from here we can go to the state space, but the identification is not that easy. So this is the work that we did for 2 years for NG grid. Okay, NIA project. That is, so what we need to do, we inject some current and we get some voltage, but we need to have these parameters estimated. So you got only two currents and you get two Y variables. How can you find 4 unknowns from these two equations? So you need to have two sets of measurements. Putting here another sets of measurement and getting another set of voltage and try to find out what would be the Z. So this is the idea that came from Dusan Goriovic from Virginia Tech in that work, the paper. So that if you apply here through this vector fitting, you can find some kind of transfer functions and then A, B, C, D. So now we do that impedance estimation by vector fitting, average model of the voltage source converter with phase lock loop and current control. And this, you see that all those impedance magnitude and then their phase angle. Right. This is Martha Molinas from NTNU's group. They did this work, beautiful work. And this is what I was telling the guys. This Kiel, University of Kiel had some presentation yesterday, right? I was talking about that. So this is that, you see that how very nicely it is matching from the measurement to the vector fitting. Then what I do, so we did this, we reproduced this on a PSCAD. So PSCAD based simulation, and then you find this and you do all you apply this additional signal of different frequency, and then you find out through this the impedance. So this all match very nicely, measurement and fitting. So what happens when we bring in the voltage source converter with phase lock loop and current control, including the delay. When we bring that, the current control that include the delay of the switching delay, switching dynamics, then there are some discrepancies between the fitting and the measurement based approach. So vector fitting does not always give you the exact sort of impedance spectrum. We now include the detailed control structure Now, if we have a modular converter with the capacitor charge balancing circuit of each of these, so now you see bringing their detailed control structure, not average model of the converters, how they all differ. This is the measurement again, and this is the fitting. So this is very much, um, differing. We now with this the control with strong grid. If we do with a strong grid, there we see that there are some matching, but this time you see that here the jets are not matching. So what we did, we went with the admittance approach rather than vector fitting approach. Like we had V is equal to Z into I. So I current was our injected quantity, and then voltage was measurement. So rather than doing that, we went to the I is equal to YV. So we applied a voltage signal of varying frequency and sample the current, and then find admittance. So we found, the tracking the admittance is a lot easier in vector fitting than tracking the impedance. So that's how we were shifted to this Y, and then we got this for that. The moment we go to a weak sort of say grid, that is high value of the Thevenin impedance, now there are again some the mismatch with this admittance estimation. So then we do the impact of the time sweep. So what happens? We have the whole EMT model, and we have excited that the converter, the STATCOM is producing the voltage, etc. And on top of that, we have added one voltage source of a variable frequency. That variable frequency, yes. So that variable frequency voltage source, and whatever current we get from that, we do the sampling. And on that sample, we put actually the impedance estimation algorithms. So there you have a STATCOM MMC with a carrier frequency 360 Hz, and if each arm has about 44 power modules to build the voltage, so the effective update frequency has to be 15 kilohertz. So that means for every 63 microsecond, we must finish our computations. It should be at most 63 microsecond. The sampling cannot be slow. So this is how, if we sample slowly, like a time step of 100 microsecond, you see that they don't, they are very erroneous. And with a sample of sampling time of 10 microsecond, this is very good that way. So these are all the things that we have been finding, and then how the impact of this converters switching delay have on the stability margin. So this is this short circuit ratio versus the X by R. So this line actually, so this side is unstable zone. This is the stable zone. If we have an average state space model without any delay. Now more and more delay we include, that you see the stable zone is now shrinking and unstable zone is now expanding. So this is a clear, sort of correlation that the converter detailed control dynamics, how it influences the overall stability of the system. Now we do this, that's for STATCOM we did. Now we put the STATCOM and WinFarm and synchronous machines all in a network. So then what happens? This is a 10 machine 39 bus system. So we have big silent versions, as well as we can have a PS card version, synchronous machines with all AVR, etc. Then we do EMT simulation PS CAD and find out the response. Phasor approach, big silent, we found out the response, so that we make sure that whatever module that etc. we have done, their models are correct. And then we put a STATCOM here in this and WinFarm there. So now what we do, we keep some synchronous machine, and for the network, we try to do some simplification of the network by just nominal pi. So what we did, we have 1, 2, 3 zone. How we got this zone is the MBA level, the fault level. Fault level here, you could see here, the fault level is very, very low. Means this part of the network is very weak. This part of the network is very strong. Maybe there are a large number of synchronous machines here. So accordingly, we put all these buses as 2 or 3 equivalent, etc., etc. we do some static equivalencing here. And then we found out this is going to be our network wind farm. And we put actually the statcom, and then this side is synchronous generator. So this, when you flip it, so this is the grid with synchronous equivalent generator and the wind farm and the statcom. And then as we vary the fault level, that is from the synchronous generator, this ZTH, how some of the poles are moving. So strong grid, this side all the poles are on the left half. Weak grid, if you go to the 530 MVA, then you see that we are crossing this. So weak grid, and now the interactions from the wind as well as this is now more visible. So that stability analysis for varying grid strength, wind farm only. So this is this, and then this is frequency domain. This is time domain PSCAD, and you see that how those things are as it moves here, how they are becoming unstable. So then we impact of the statcom on the AC voltage loop gain. The statcom has got its control gain, etc. And if we change that control gain, how it impacts this. So again, some of the frequency with the control gain, it's going to that side. So that is this. So finally, we put everything, statcom, wind farm, network all together and carry out the participation factor analysis of some of the mode. And now you see that as the control gain of the statcom changes, how wind farm and statcom relatively participate and how they differ, etc., etc. So that is again the interactions issues. And PSCAD results, after we did all this for a simplified model, we now go to the full 39 bus systems on a PSCAD and put all those statcom with the controller gain, etc. And then we do these simulations. And there you see that voltage at node 28, 29, reactive power and reactive power from the wind turbine generator and statcom, how they become oscillatory with high gain of the or fast response time of the statcom. So the inside is the admittance estimation based stability assessment tool, takes care of the detailed dynamic model of the multimodular converter, including the control circuit delays as well as the capacitor charge balancing dynamics. The model is comprehensive in assessing the network stability impact of control delay, varying network short circuit capacity, fault right through capability of these devices during network events. The approach has demonstrated that the real network operability margin is significantly lower. The real network stability margin is significantly lower in low short circuit cases when compared to the same obtained through the time average simplified model of the device. So that means when there is a grid connection applications of a wind farm, so in the wind farm and also the interface statcom, like how you see I've got statcom. Now, if they represent this everything as an equivalent voltage source, so many things are not coming up. And once those detailed dynamics are included, how the operability of the network is shrinking, how the stability margin is shrinking, that is important. So grid codes should take care of it. And the insistence should be that, guys, do the full dynamic simulations with a full model and so on. So that is the impact of the detailed control on the stability margin and so on. So it's very much required to have the detailed model of converter-based device when performing grid connection studies in electromagnetic transient time scale. Stability assessment studies need to be performed for varying grid strength, short circuit level at the point of connections, as well as transmission voltage level. So TNO and TSO should insist on various other parametric sensitivity studies regarding key control schemes, interface PLL technology, etc. So they must reveal what are the PLL technology, etc., what are the topologies and so on. And that specification should be amended with these requirements so that any connection study adheres to these detailed specifications and so on. So this is the guy who worked on that, Nicholas, and some of the work are here. Black box impedance based stability assessment of dynamic interaction between converters and grid. And he is working now in a consulting organizations. So that's the thing. I think I'm taking a bit of time. Just
So, who would like to